Welcome back. In this video we will see how to change parameters in your models to investigate, for example, stability of your system when changing multiple parameters. So let's open the tutorial 5 and we will look at the parameter study with the reflective boundary. So the system is quite simple. We have two reflection coefficient of -1 at both ends that acts as an open end. We have two ducts that are placed upstream and downstream respectively of an area change. So the area change is really simple, no losses, no inertial effects, just a simple change of areas. So how can you change the parameters? Well, if you are just looking at one or two parameters, you can simply edit yourself in the graphical user interface in your Simulink model, save it, and run the model. But if you want to see the impact of many parameters, or if you have many inputs, it can become really tedious. So you want to automate that. You have different methods. Let's look at the first one. So here we want to investigate what's happening when we change the position of the area ratio. So we will keep the total length constant of 1 meter, and we will put this area ratio from the inlet to the outlet and see how that impacts the first two eigenmodes, which means that the lengths of the upstream and downstream ducts will be changed from 0 to 1. So to do that, we define our max frequency and we create our TX model, which is simply we read the file. Then I defined my two vectors that are the parameters we will be imposing. So an upstream length that changes from 0 to 1 with 0.025 step. And the downstream length is 1 minus the upstream because we want to keep a total constant length. And the key thing, so here I create a loop for all my different lengths. A lot of this code is just for plotting purposes. I want to track the eigenmodes, identify them properly. You can look into the details, but it's not important for this example. The key thing is this line here, where we say we want to change param. So change the parameters of our model. So we want to change the parameters of this, which is our TX model, and what we want to do is here the naming is important. So the naming in your model when you set up your network at the beginning. If you want to use explicit names, it can be useful, especially for these cases of changing parameters. So for the duct upstream element, we want to change its length, so .l, and it has to be the value L upstream, and in the loop look at element I length. So update the length of the upstream and at the same time update the length at the downstream. So here it will change both parameters at the same time, then it will update the this element, so the variable, so the TX model will be updated. Here we changed only acoustic parameters. The lengths we changed have only an impact on acoustics. But if you change, for example, area ratio, that will impact the mean velocity downstream of your area change. So again, TX would do automatically will automatically update the mean values, so it will redo a mean value computation to update your model. So if you use changeParam with multiple parameters, it will change them all at the same time. So if you want to change one then the other, you have to call the function 2 different times. Then we extract the eigenvalues. We filter the eigenmodes that are outside of the window of interest, and then we will just plot the growth rate or the cycle increment and the frequency. So cycle increment is just another way of looking at growth rate. Let me briefly give you an introduction on that topic. So Tx uses the convention exponential st, s being the Laplace variable, which is sigma plus I omega. So growth rate sigma and the frequency. So it means that the exponential st term can be decomposed into a growth rate term and I omega or angular frequency term. Now, if we look at what's happening after one period of your eigenmode, we look at exponential st plus capital T, one period. Again, we decompose between the sigma and I omega term, and this exponential I omega t plus one period. So this term is exactly I omega t, because by definition, this is periodic of period t. And the cycle increment, we define it as how much has the amplitude changed after one cycle. So between time t and time t plus one cycle, how much different is the amplitude? So we take the absolute value of those two terms, and we take the difference and we normalize by the absolute value at time t. And if we do the math, it's simply exponential growth rate times one period minus 1. So with the convention of Tx, it would be exponential real part of s, so the growth rate, times 2 pi divided by the imaginary part minus 1. So it's convenient because you can easily interpret it. If gamma is greater than 0, it means that your mode is growing. If it's 0, it's neither growing nor decaying. And if it's negative, then you have a decaying mode, so a stable mode. So it's another way of looking at growth rate. So let's now run the code and see what happens. So we obtain those figures. We have growth rate as a function of the position of the area change, cycle increment, and dimensionless frequency. So what we can see is that the position of the area change has minimal impact on the frequency of the oscillations for both the first two eigenmodes. But if we look at cycle increment, for example, no matter where we have the area change, the cycle increment is above 0, which means that, let's say here, if it's at 0.5, we have exactly 0. So it would be stable, but for all other positions, the fundamental mode would be unstable, and the first harmonic is also always unstable unless at those two positions. And that is really strange because we have two ducts and one area change with no losses, and we have no source of energy in the system. Still, it is predicted to be unstable. How is that possible? So this is not the topic exactly of this video, where we want to change parameters, but it's the opportunity for me to draw your attention on the modeling choices you make, and that to the fact that if you're not careful, you can obtain results that have no physical sense. Here we used a reflective boundary of -1, which is equivalent to an open end, but that's only valid for a 0 Mach number. Here we have some mean flow. Mach number is 0.15. And this is the problem, because now we have boundaries that do not preserve acoustic energy. That is the conclusion from this figure. We have growth rate or cycle increment positive, we have growing modes, but we have no source of energy in our system, so that can only come from the boundaries element. I can give you a sneak peek of what's happening there. If you want to derive a boundary condition that conserve energy, you can do that, for example, with the Bernoulli equation. So you say that at your boundary, you have P plus 1/2 of rho U square is equal to P infinite, because when you are far from your boundary, you have no velocity or no mean flow anymore, so you just have your pressure. So this is the left-hand side is for the condition at the open end, and this is the condition for the surroundings. We assume there's no fluctuation of pressure in the surroundings, and we do a linearization to first order in Mach number, and we obtain this equation that P prime over rho C plus Mach number U prime is equal to 0. If we convert that into F and G waves, that gives us this equation. So if we had no mean flow, Mach number would be 0. We would have P prime is equal to 0, which is an open end. F over R equals -1. So F plus G is equal to 0. However, as soon as we have some mean flow, to be energetically consistent, we cannot use R equals -1 anymore. We have to define the reflection coefficient to account for mean flow. So in the context of an outlet reflection coefficient, we would have this expression, and for an inlet this one. Again, we can verify that if Mach number is 0, we retrieve R equals -1. So, long story short, you can use the reflective end element, but be careful on how you use it, because you might be introducing spurious energy in your system if you use it with a Mach number. On the other side, you can use the open end, for example, from TX. So in the library, we can verify that we have two elements that are open end and closed end. Those two are defined in a way that no matter your mean values, both boundary will be energetically consistent, so you will not create spurious energy. We can check that by rerunning the same code, but with the model where we use open boundaries. And if we do that, takes a bit of time to reproduce the figures again. And we obtain those two figures. So again, let me put that again in the correct order. So cycle increment and frequency. Again, the frequency does not change much when we change the position of the area change. And it has a slight impact on the stability. But if you look at the scales, it's 10 to the power -4, so almost 0, which is consistent with the fact that we have a system with only passive elements, no energy created. We have no dissipation because we have no losses, so growth rate is 0. So to summarize this small digression, be careful with the elements you're using and your modeling assumptions. Now you have another method to change parameters. It's with the parameterStudy function. So again, you create your TX model. parameterStudy is behaves a bit differently. So again, you say which system you want to, or which TX model you want to change, and you give the parameters you want to change and the ranges from where to where they change. However, in this case, parameterStudy does not change both parameters at the same time, but it will create all possible combinations of the parameters. So here we change 2 parameters. I have 5 values for each parameter, so it's 25 combinations. But if you would change, I don't know, 5 parameters with 10 values for each, that would be a lot of combinations. So this function is rather to be used when you want to do Monte Carlo simulations. Or if you change only 1 parameter and want to quickly have a sneak peek on what's happening, the interesting part of this function is that it allows you to store all TX models. So instead of updating the current TX element or variable, it will create a new one, and you can store all that in an array. So it is convenient if you want to plot then everything at the same time. However, it can be also very costly to store hundreds and hundreds of TX models. So be careful when you want to use this parameterStudy. Here is the example. We plot the parameter map for all possible combinations, and since we have all the TX models and not one that is updated, we can plot all the eigenfrequencies directly in one command line with the plot pole map function. Here again, we can see directly that we have many modes that are unstable, which is unphysical. So recall what we just saw. And be careful with your modeling assumptions. So to summarize, you have 2 functions: parameterStudy, which is rather suited for Monte Carlo simulation when you want to try all possible combination of parameters, and changeParam, which allows you to change as many as you want parameters from your system, and it will automatically update it.